Welcome to Chapter 10, the Part 7 Screencast for liquids, solids, and phase changes. At the end of the previous screencast, we had been dealing with vapor pressure as a function of temperature, and we looked at the vapor pressure of water at different temperatures, and we had the graph of it. So we're going to pick up with that analysis, and here we have vapor pressure data at various temperatures ranging from 0 degrees Celsius or 273 Kelvin on up past 100 degrees Celsius. And notice that as the temperature increases, the vapor pressure also increases. Now note that the temperature is basically going up by 10 degrees Celsius or 10 Kelvin. And while it does the steady incremental rise in temperature, the pressure, the vapor pressure, goes up in increasingly large jumps or increases. If we graph that, it has the characteristic shape of a vapor pressure or a gas-liquid equilibrium line curve, as you can see right here. And here's a graph and the data once again. And the question is, how are vapor pressure and temperature related? Are they directly proportional? Are they inversely proportional? Or are they related in some other strange mathematical way that you're probably going to have to learn about? And if you've been paying attention throughout this course, you certainly can see this is not direct. It's not inverse proportionality. So it's going to be some other kind of mathematical relationship. And yes, you will have to learn about it now. So here is our data once again, temperature versus vapor pressure. But what we've done is we've worked with the data a little bit. And here is a column where we've taken the natural log, ln, of the vapor pressure values. And we've taken the temperature values in Kelvin and taken their reciprocal, so 1 over temperature. And the reason this was done, and this is a pretty common technique used throughout science, is when we have a graph of some data that's curved, we often see if we can linearize it. In other words, see if there's any way we can manipulate the two variables and end up getting a straight line graph by somehow doing some different things to either the x value or the y value, in this case the p or the t values. And it turns out, and it might require some trial and error, but it turns out that in this case, if we graph the 1 over temperature in Kelvin versus the natural logarithm of the vapor pressure, we end up getting a very straight line. And the mathematical relationship that gives us this straight line is known as the Clausius-Clapeyron equation. And here it is in all its glory. The Clausius-Clapeyron equation says that the natural logarithm of the vapor pressure is equal to the negative enthalpy of vaporization for that substance over the gas constant R times 1 over the temperature in Kelvin plus some constant. And note, this is a linear relationship. You're probably most familiar with seeing y equals mx plus b representing a straight line. But note that if y, in our case, is natural log of p, and if x is 1 over t, then we get a straight line with slope of m equals negative delta h over r, and y-intercept of c, which is this constant. Now, there's a number of things we can do with this. One is we can, if we know pressure and temperature values, vapor pressure at a given temperature, we can use that to determine the enthalpy of vaporization for the substance. We can also use it to answer questions like this. So example 16 is that for benzene, which is C6H6, its normal boiling point is 80.1 degrees Celsius, and its delta H of vaporization is 30.8 kilojoules per mole. And the question is, what's the temperature at which benzene boils? What's its boiling point in Denver, where the atmospheric pressure is a fair bit lower than at sea level? It's 0.823 atmospheres. So notice we have vapor pressures, we have pressures and temperatures, and we have delta H values. So that sounds like maybe we could use the Clausius-Clapeyron equation to answer the question. Now, there's a technique we use to do this, and in general, the Clausius-Clapeyron equation says that the natural log of the pressure is equal to negative delta H over R times 1 over T plus a constant. But of course, what this means is if we are at one particular pressure temperature point, and we'll call that state 2, or if we're at a different pressure temperature point, which we'll call state 1, this equation holds, but at state 1 it holds for pressure 1 and temperature 1, and at state 2, which might be which will be some different temperature and therefore different pressure, the relationship holds for P2 and T2. And now notice, this means we have two equations, and these two equations have two different pressure temperature points. And if we take these two equations and manipulate them a little bit, and here what we're going to choose to do is to subtract one equation from the other. So we'll subtract equation 1 from equation 2. That's why we put equation 2 on the top. And when we do that, we subtract left sides of equations, we subtract right sides of equations, and it's still an equation. So on the left, the natural log of P2 minus the natural log of P1, and on the right, that equals negative delta H over R times 1 over T2 minus negative delta H over R times 1 over T1. And if we do a little bit of mathematical manipulation and remember the properties of logarithms, we end up getting the natural log of the quotient P2 over P1 equals negative delta H over R times the quantity 1 over T2 minus 1 over T1. So we can now apply this to the equation, to the problem we were just given, and we're going to choose P1 and T1 to be the normal boiling point, and 80.1 degrees Celsius is 353.3 Kelvin, and normal boiling, remember, means at normal sea level atmospheric conditions, so the vapor pressure will equal the external pressure of 1 atmosphere. And we need to find the boiling temperature at the pressure conditions in Denver, which is 0.823 atmospheres. So we know P2, but we don't know T2. That's what we're going to find. Here is our Clausius-Clapeyron equation in the 2-point form, P1, T1, and P2, T2. And if we plug in all of our values, we get the natural log of the quotient of P2, which is 0.823 atmospheres, over P1, which is 1 atmosphere. Delta H of vaporization is 30.8 kilojoules per mole. And since we're going to use the gas constant in the form with joules as one of the units, we're going to use 8.314 joules per mole Kelvin. Therefore, we want our delta H to also be in joules, so it's 30,880 joules per mole. And then we have 1 over T2 minus 1 over 353.3 Kelvin, which is T1. And so notice what we're trying to solve for now is T2. And this is something you should know how to do mathematically. For our purposes, we're just simply going to say you do some math and you get the answer. The suggestion would be make sure you know how to get from the setup equation to the answer. And of course, usual thing, you have to isolate the unknown variable, in this case T2, which means you have to undo all these other things. So you have to remember how to deal with the natural logarithm, what's its inverse function. And if people have questions on that, I can post something with the detailed step-by-step solution. Okay, so a vapor pressure graph for a given substance is going to show pressure and temperature points at which the liquid and gas are in dynamic equilibrium with each other. So here it is for water, here's one for ethanol, there's one for ether, as we saw in a previous screencast. Now, if we do this for not just liquid and gas and their equilibrium, line, but we also do this for solid and liquid, as well as solid and gas, and even solid and solid in some cases, we end up getting a graph that looks something like this. So basically, we're getting pressure and temperature data points for the various phases and the various equilibria for a given substance. And this is what's called a phase diagram, and it has lots of information that you should be able to interpret. So here's the phase diagram. Actually, this is for water. And notice here is the equilibrium line between the liquid and the gas. So that's the vapor pressure line we've seen already. Gas to the right and below that line, liquid to the left and above it. But now we also have a solid liquid equilibrium line and a gas solid equilibrium line and a few other things. So what you should be able to do ultimately is, given a phase diagram, be able to apply and interpret it to determine states and changes of state. And we'll do a couple examples of what is meant by this. And we'll also go through a little bit of what these various other things that are listed on the graph are, like the triple point and the critical point. Okay, so gas is in the reasonably high temperature, lower pressure region. Solids tend to be lower temperatures and sometimes higher pressures. Liquids tend to be in between that. These are phase separation lines between them. And in the case of water, the solid liquid line has a negative slope. More on that in a little bit. In most substances, the solid liquid line actually has a slightly positive slope. So solid here at the lower temperature, liquid in between, gas at higher temperature. Here's the solid liquid equilibrium phase boundary. Here's the liquid gas equilibrium phase boundary. There is a solid gas equilibrium phase boundary. And you should then be able to, given a phase diagram, answer questions like this. So, what phase is water in at 200 degrees Celsius and 200 atmospheres? Now, you're probably not born knowing this, but if you look at the graph, there's 200 degrees Celsius, there's 200 atmospheres, and that point pretty clearly falls in the liquid region. What happens to ice as pressure increases? Well, ice is solid water. This is liquid water. This is gaseous water. So we start with solid and increase the pressure, which means going up. And noting the slope of this solid liquid line, if we start with solid and increase the pressure, eventually, if we go straight up, we're going to cross the solid liquid line, which means as we increase the pressure, solid ice or solid water actually turns into liquid water. In other words, it melts. And most substances, it's the other way around, but for water, if you apply pressure, you actually force the solid to turn into a liquid. And basically, if you hang a wire with some weights on it over a block of ice, it will ultimately cut through the block of ice. The ice will refreeze after the piece of wire works its way through, and you can actually cut through the block of ice without ever having actually cut through the block of ice, because it stays intact. You just cut through a little piece of it at a time, very gradually. Okay. There is a triple point for water and for most other substances where all three phases, solid, liquid, and gas, can coexist at the same temperature and pressure. So here is for water at 0.0098 degrees Celsius and 0.0060 atmospheres. We have a container where we have boiling water, we have ice, and we have gas, all coexisting, but only at that exact temperature pressure point. And one more thing is there's a critical point, and that will be explained in a cool video by this outstandingly coiffed guy here, which will be posted on the website, and we'll talk about supercritical fluids a little in the next screencast.